Not me. I don't want to thank anybody. No, actually, I do want to thank people. First, let me thank the organizers for a great conference. Thank you for having me and allowing me to present. Uh, and second, let me thank the keynote speakers. I know and I'm sure many other people here feel very, very fortunate to have benefited from all your work over the years, your seminars, your comments, your teachings. I mean, the number of people who have gotten these amazing jobs that are, interesting jobs, influential jobs, both in and out of academics, as we've heard today, is just amazing. Uh, I will also lay claim to be maybe the most fortunate person here is I actually had three of the keynote speakers on my dissertation committee as I overlap with John Rust at the end when he came to Yale. I mean, I guess it's possible that with outside readers, some of you may have had four and you can beat my record, but I lay claim to being the most fortunate one. Anyway, thank you guys very much. Okay, so I'm going to talk today about something that Jan, who wishes he was here, I'm sure he also feels the same way as me about that stuff, have been thinking about for a few years now. It's about estimating production functions in the context of imperfect competition. This is important. I don't think I need to argue this here, that many markets are characterized by imperfect competition. Uh, Estimating production functions can also it can inform a lot of interesting current policy questions. In particular, I'm talking here about this supply side approach to markup estimation that's been sort of repopularized by Jan and co-authors. Though I should say, just in the context of this conference, goes back many, many years. I mean, the Hall work is often cited, although that's maybe a little bit more macro-y. But if you go back in the old IO literature, Gallup and Roberts, is a paper that essentially was estimating a production function. And once you estimate a production function, you know the costs of variable inputs, you know marginal costs, you see prices, and you see markups. Now, they were using it to assess conjectural variations parameters, and they don't have markups in the title, but it was essentially estimating markups using production function estimation. There's other papers as well. I was looking at Tim's handbook chapter. There's a section on this where there's that paper is mentioned. The papers by Applebaum are mentioned as well. Anyway, the production functions and technological relationships. So some approaches can actually be used without completely abstracting from the level of competition. So like a cost share approach could be used that has nothing to do with competition, that can be done without having nothing to do with competition, but that requires some strong assumptions. But we're going to sort of argue that more commonly used approaches that don't require those strong assumptions or those particular assumptions can benefit from further thought. And as you'll see here, we're going to sort of detail how sort of the standard Ali-Pecos-like approaches can be challenging with imperfect competition, and we're going to try to sort of show how maybe that can be aided. Okay. So what are the questions in this paper? So as I just alluded to, can we make Ali-Pecos style approaches with imperfect competition more feasible? And we'll see the answer to that is yes, at least in some common models, but it's going to require a little bit of work. I'm not going to talk, that's sort of the first half of the paper. I'm going to talk not that long about it today, though. The second part is making the point that markets characterized by imperfect competition can actually provide helpful variation that can help identify production functions that can, in some cases, address things that have been problematic in the production function literature regarding identification. And interestingly, the answer to that is yes, and that's not only relevant for Ali-Pecos style approaches, but also for some alternatives that have been used, things like the dynamic panel literature, which have often been applied to production function estimation. And so we'll investigate that source of identification. Okay, so I'm going to do a quick 5-minute recap of Ali-Pecos style approaches. And again, so I call it Ali-Pecos style approaches because there's this is parts of Ali-Pecos, parts Levinson-Petrin, parts stuff that I've done is just sort of a little bit of an amalgam of all this stuff, but this is all essentially derived from the Ali-Pecos paper and the techniques that were introduced there. We have a production function. Throughout the paper, F is going to be fixed inputs. V is going to be a variable input. In this literature, we typically think about allow there to be two shocks to output, one being omega, which is the productivity shock of the firm, That's going to be the unobservable that's going to cause endogeneity problems because firms are going to either fully or partially observe omega when they choose F and V. There's also going to be a measurement error, an epsilon, which is going to probably easiest to think about as this being classical measurement error in Q. And so that's not causing any endogeneity problems. The endogeneity problems are all being caused by that productivity shock omega. Right? And so this is essentially the first stage of the Alley-Pecos type of an Alley-Pecos type approach is to specify a decision of the firm that depends on that problematic omega and other observables. So for here, we'll think about firm's optimal choice of the variable input V. And in some models, you might write down if the firm is choosing V after its fixed input has been chosen and after it knows its productivity shock, that choice of V may depend on that productivity shock and that level of the fixed input. And if that is true, that is that if there's only this scalar unobservable in that equation determining the firm's optimal choice of the variable input, and this thing is strictly monotonic in that omega, you can invert it, that is substituted in here into the production function, and you can consider estimating this equation in the Alley-Pecos case, treating this thing semi-parametrically, and not here estimate the betas necessarily, but at least get estimates of these epsilons. We'll call them epsilon hats. One thing to note here is that, and I would argue is one of the key contributions, one of the many key contributions of the Alley-Pecos paper, is the idea here that non-parametrics can substitute for things you don't want to deal with. Right? This V function may be very complicated. It depends on demand. It may depend on whether firms are colluding or not and how much they're colluding. Right? If this was a dynamic thing, it might depend on lots of things relevant to the dynamic optimization of the firm. Alley-Pecos is able to deal with that by just treating this thing semi-parametrically, and so he's able to estimate, in theory not yet, but potentially estimate a production function without having to fully specify those other parts of the model, like the demand system or like how firms are competing. Anyway, so this is sort of like the first stage of Alley-Pecos. You get those epsilon hats, and they can be then subtracted out of the dependent variable here. Now we only have one unobservable here. Of course, this is maybe the tougher one because it's causing the endogeneity problems. This is now the quick recap of the second stage of Alley-Pecos. So what are they going to assume? They're going to assume that this omega productivity shock is a first-order Markov process with innovations that are not predictable by the firm. That is, the firm is going through time. It sees its current omega, but doesn't know its future omegas. So that's essentially what this is saying. If I'm at t minus 1, I know my future omega is going to be the depreciated current omega plus an innovation term, the 6c. Right? This is essentially saying that that innovation at t was unpredictable at t minus 1. Right? And then we have this model. We condition on a guess of the parameters. You can infer what the implied omegas are. You can infer what the implied xc's are from the implied omegas. And then you can potentially estimate the structural parameters with GMM based on this. That is the assumption that the innovation term in the productivity shock is mean independent of the decisions that the firm made before that productivity shock was realized. Now, what is specifically in here is going to depend on the exact timing and information set assumptions one is willing to make. Like sort of the classic one in Alley-Pecos would be that in this ijt minus 1 is your lagged variable input, but your current fixed input. Essentially what that is assuming, that's a timing assumption that's assuming that the fixed input at period t was actually decided at t minus 1. And therefore, that fixed input at t is going to be, or the innovation term at t is mean independent of that fixed input at t. I'm illustrating this with the Cobb-Douglas and AR1, but everything is applicable more generally, including like high-order Markov processes. Just one thing about this, I would call this second stage, yet another key contribution of Alley-Pecos, sort of, I would call it a timing information set way of addressing endogeneity problems. I would describe it sort of generally as like sort of like a panel strategy, right? We all, of course, know fixed effects. What does fixed effects do? It's sort of taking the error term and decomposing it into a part that you're going to allow to be correlated with the explanatory variables and a part that you're going to assume is not correlated with the explanatory variables. This is essentially doing the same thing. It's just the decomposition is different. We're going to see, say, part of the omega, the part that comes from last period, is correlated with capital, but the innovation part is not correlated with capital. So it's essentially just a decomposition, just like fixed effects. And it's a decomposition that, at least in the production function literature, works a lot better. You estimate these things using fixed effects, you get crazy results. You estimate it using this sort of different decomposition based on these timing information set assumptions, and you often get much more reasonable estimates. Okay, so back to the questions. Can we make the Ali-Pekka style approaches with imperfect competition more feasible? And can markets characterized by imperfect competition provide additional exogenous variation that can help with identification of production functions? We're going to answer those questions. And I just want to make the point that we're going to do this while preserving what I said before was a key characteristic of, I would argue, of Ali-Pekka style approaches, that the production function can be estimated without fully specifying the demand side of the market or conduct. Why would that be the case? Maybe we don't observe enough data to do this. Maybe we don't observe prices, or we don't observe price variation or exogenous price variation that's sufficient to identify demand. Or we just don't want to make the assumptions necessary to fully specify the demand system or to fully specify conduct. So, and some of the stuff in this paper you could probably use even if you could estimate demand as well, but I think you'd be doing things differently. I mean, that would obviously help if you were able to identify demand as well. But the way to think about this is we're trying to do it without having to specify that. And again, sometimes using this semi-parametric approach to do that. Okay, so in doing that, we're going to be the questions, we're going to be focusing on two aspects of my sort of recap of Ali-Pekka's. First is that input demand function that's getting inverted, right? And it needs to satisfy that scalar unobservable assumption and is going to be treated non-parametrically. So there's going to be that, and then also this moment condition, which I also introduced before. In both these cases, there's going to be questions about when there's imperfect competition, what else needs to be in these things? So that's essentially what I'm going to be discussing. What additional variables need to be in here? What additional variables can be in here? Right? And it's interesting because these additional variables are going to both help and hinder things. Up here, they're going to be a little bit of a problem because they're increasing the dimension of a non-parametric function. Here, they're potentially helpful because they're essentially more instruments. On the other hand, when you stick lots of stuff in here in a GMM thing, you get lots of over-identification, and that can lead to some problems as well, and we're going to sort of think about that. Related literature, obviously the entire production function literature, which I'm not going to go through. One interesting thing is we go through is you'll see that some of the stuff that is here ends up relating back to the demand literature. And some of it will be reminiscent of that, as we'll see. Okay, so Ali-Pekka style first stage with imperfect competition. First, the point I want to make, and this relates to what I was saying before, is that Ali-Pekka style first stages can incorporate imperfect competition, but it's a little bit challenging. And why is that? Well, you can sort of take two approaches, right? First, again, we're trying to think about an equation that determines the firm's choice of a variable input. Right? And it's going to depend on your own productivity shock, your own level of the fixed input. If you're in a model where you have competitors, it's natural to think about this also depending on the same things for all your competitors, because that affects your competitors' marginal cost. It's going to affect your competitors' choice of V's, and through competition, that's going to affect stuff. So one way you could deal with this is by sticking in vectors of your competitors' productivity shocks and fixed inputs. This ZT is just intended to represent like market-specific observables, like market-level demand shocks. So that's one way to do that. Of course, that's going to be a little challenging because now this is going to be very large dimensional. Now, another way to do it would be to not have this stuff in here, but to instead index that V by T. That's to say we're going to estimate a separate V function for each market. And the intuition here is that this is now just saying if me and Gunter are in the same market, because we have the same competitors, if we have the same omega and the same F, we're going to do the same V. right? If we're in the same market, of course. If I'm in a different market than Gunter and we have different competitors, that's not going to be true. So either we sort of control for competitors explicitly in here, or we sort of control for it implicitly by putting a T here. And then yeah, if Gunter and I are in the same market and the two relevant variables for us are the same, obviously we're going to make the same choice of V, right? Excuse me? Which market? That's a good question. I don't Okay. Yes. Which would be different? Yeah, so VT, it's going to be a different function across different markets, right? Gunter and I are in one market and we have the same things. We're going to do the same thing, right? But that's different than what, you and Jeremy do in a different market. Yes. Huh? I mean, here you can assume that this is the same across markets, right? Okay. I'm saying if you take them out, you need to assume they're different across markets, which sounds like what you're saying, but maybe I'm missing something. Yeah. This cannot hold for every model of product differentiation. I will agree with that. So if you're thinking about that, then I'm not claiming that this always works, but there are models under which this works. Like think about a symmetric logit model. So yes, that's a good point. And that's going to sort of come back to what we do here. Okay. Anyway, in the context of simpler models, we're going to show cases where even in the simpler models, these are complicated, either because you have this big non-parametric thing, object, or because you have to estimate lots of non-parametric functions, a different non-parametric function for each market. And when we're thinking about imperfect competition, we're not thinking about a lot of firms per market. So the first half of our paper is basically going to find models and conditions under which we can simplify this stuff using some lower dimensional sufficient statistics. I'm just going to basically go through the results here of some models we show where this works. And again, this is just a limited set of models, but it's even simpler than the prior page. Just one thing about these models like Cournot, differentiating product, Bertrand, where again, these are a little bit different than the standard ones because there's this underlying production function. And we're thinking about games where the fixed input levels and productivity shocks are given for all firms, and firms are choosing the variable inputs. In the Cournot game, it's essentially choosing Q. In the Bertrand game, it would be choosing P. There's an equilibrium set of quantities, and every firm has to employ the V that gives them that quantity given their fixed input and productivity shocks. So those are the sort of games we're thinking of here. Anyway, what's the point? Let me focus on this Bertrand differentiated product logit. These models by the way, have sort of arbitrary demand functions. So this is the utility function in our logit-like models. This is a demand function in our Cournot-like model. Again, we're not going to specify what those things are. These equations are going to hold regardless of what the utility function looks like in this logit model, regardless of what the utility function looks like in this nested logit model. Anyway, in the logit model, what this is essentially saying, this sufficient statistic is saying, is that across markets, me and Gunter can be in different markets. If we have the same product characteristics, the same productivity shock, the same fixed input, and we face the same market level supply shocks, if in equilibrium, our competitors are producing the same total quantity, then in equilibrium, we must be using the same amount of the variable input. That's the nature of these sorts of results. And so that means that you could use this in an Ali-Pecos style inversion and just have this scalar in here rather than everything of all the firms in the market. And there's no T here. So it's essentially about reducing the dimensionality and in what cases you can do that. Can do it in a nested logit model. Instead of one sufficient statistic, you get two sufficient statistics. Again, it's not super general. You could not do this with random coefficients models. Those are too asymmetric in how product differentiation works. But in a set of models, you can do this. And note that this all works with any general form, lots of general forms of collusion. So if you took a model where there are profit weights, right? Those profit rates, as long as they're a function of observables, these things would all hold. Right? And so again, the non-parametric, treating V non-parametrically is getting you a lot. You don't have to specify the form of demand, and you don't have to specify the nature of competition. And so basically, again, this is the point of the first half of the paper, that these equations can be used for a low-dimensional first-stage Alley-Pecos style inversion. There's a little bit more work, and you can look at the paper for that. Okay, so the second half of the paper is going to think about something different, which is considering how imperfect competition can sort of aid in the second stage estimation of, for example, Alley-Pecos. Right? And again, these are using moment conditions like this, that this innovation term is uncorrelated with functions of these instruments, the things that were decided before it was realized. As I alluded to before, this is relevant for Alley-Pecos second stages, and it's also relevant for other sort of approaches that are used to estimate production functions, like dynamic panel, like some stuff that I've talked about. These alternative methods, they don't have a first stage like I just talked about, but they make additional other assumptions. So it's sort of a trade-off of assumptions. Okay, so what are the questions going to be here? So the question is going to be sort of what's in this ijt minus 1? How might imperfect competition change that? Question is going to be, does this moment condition identify theta? Because there are some important results that say under some cases this will not identify the structural parameters. And then what should M be? And that's sort of like an efficient instruments question. One thing to note here is that T here can both, sort of trying to be parsimonious here, T can index either geographic or temporal markets. So you could have markets across space, you could have markets, or you need some markets across time, but you could also have markets across space. And of course, anytime there's T and T minus 1 in the same equation, that's the same market in different time periods. Okay, so first off, what are the typical moments? What are the typical things used in here? Right? As I alluded to before, probably the most typical in these literatures is to use current F, because again, this timing assumption that F was decided in T minus 1, lagged V, because lagged V was decided in T minus 1, and lagged productivity shock. Essentially, again, this is assuming that capital is a fixed input and labor is a variable input, essentially. Right? And traditionally, in doing this stuff, the instruments, these things for firm J only come from firm J. Right? What we're going to be thinking about here is the idea of thinking about things in here related to J's competitors. And so that's the main point of the second half of the paper. But before doing that, but first, I wanted to just talk briefly about an important result by this Gandhi, Naravar, and Rivers paper. And this is getting into whether that moment even identifies the structural parameters. So they have this result that shows basically that if firms are choosing V to maximize profits in perfectly competitive markets, if there's no variation in the price of V across firms, and V is a non-dynamic input, which we've sort of been assuming throughout this, then actually that moment condition I wrote down before does not identify theta. That is, if you use these things as sort of your instruments, then the model is not identified. What's the intuition behind this? So let's think about a simple model where there's just two periods, 0 and 1. Let's assume everything is linear, Cobb-Douglas production, and AR1 omega process. And in particular, just for simplicity, let's assume that the econometrician observes lagged omega. And so I can stick this in for the current productivity shock and just pretend I observe this. If this isn't observable, then the only econometric error here is this thing, and I know properties of this thing. According to the standard timing information set assumptions, this thing is mean independent of F, because F was chosen last period. It's mean independent of this omega by construction. It's not mean independent of V, because it's a variable input. It is chosen as a function of the entire omega 1. But it is mean independent of lagged V, Vj0. Given that, you might proceed by doing just two-stage least squares on this. Again, it's not GMM because I'm making this assumption that this omega J0 is observed, right? What would the two-stage least squares be? It would be regressing Q on F. F is exogenous, omega J0 is exogenous, and this is endogenous, but use Vj0 as an instrument for it. So you might think about doing that. GNR's non-identification result says that in that situation, that actually will not work. Right? Essentially, in that situation that I described before, perfectly competitive environment, V is a non-dynamic input, there's no input price variation, then V0 is a completely uninformative instrument for VJ1. And so the intuition here is that the firm's optimal VJ1 is just a function of F and omega 1. Right? And so the instrument VJ0, where unconditionally VJ0 may be correlated with VJ1, it is not going to be correlated with VJ1 conditional on F1 and omega 0. And so it's not going to serve, it's not going to be an informative instrument. It's a valid instrument, but not an informative instrument. Now, there are existing ways to avoid that GNR world and the non-identification result. So some of Jan's prior work has had an observed firm-specific variable z in that variable input function that can move stuff around. GNR suggests a first-order condition approach that you can't get that coefficient. The problem is that coefficient on the variable input, but if you impose a first-order condition, that can get it. Some papers have imposed a CRS assumption, which basically lowers by 1 the number of production function coefficients you need. People have sometimes assumed there are unobserved serially correlated firm-specific variables that determine V, like there are firm-specific input prices that might be unobserved. People have done that, although this doesn't gel well with the first stage of Ally-Pecos. Anyway, the point of so there are some ways around this, but it's still sort of an important baseline result. And here we're essentially proposing or studying a different solution to this GNR world based on imperfect competition. That is, we're going to show that the nature of the competition a firm faces can essentially serve as a useful instrument for VJ1. So essentially what I am saying is Gunter's, say, capital level might be a useful instrument for my choice of the variable input. Okay, so that's essentially right here, the simplified model suggesting instrumenting for VJ1 with characteristic of firm J's competitors. So Gunter's fixed inputs, F minus J is Gunter, and potentially Gunter's lagged omega as well, because my V is likely going to respond to Gunter's productivity shock. Gunter's productivity shock today depends on Gunter's productivity shock last period. So let's think about that a little bit in terms of the validity of these instruments. So essentially, the validity of them comes from just the existing timing information set assumptions we already made, because it would be weird for this CJ1 to be correlated with Gunter's stuff, but not with my stuff. So essentially because Gunter's fixed input and Gunter's lagged omega were decided last period, they're also going to be mean independent of my innovation, my CJ1. You could actually also have this thing. It might not just be mean independent of this. It might be mean independent of Gunter's full productivity shock this period if the innovations were uncorrelated across firms. But that would be more of an additional assumption, something we can think about. Of course, on the other hand, we probably want CJ1, my shock, to be correlated with Gunter's variable input choice at 1, because that's determined in equilibrium. So that's the instrument validity, instrument relevance. In the games, we've already been thinking about these instruments are surely going to be relevant. Again, if I know Gunter's F and omega, my variable input is going to certainly depend on it. In a complete information game, it probably is going to work in general incomplete information games as well if I know something about Gunter's stuff, but not it exactly. Of course, if I don't know anything about it, then maybe it doesn't work. But in general, it's going to work. Anyway, what's the point here? The point is that these competitive instruments are another way of breaking this non-identification result. As I noted earlier, there should be some reminiscence here about the Bresnahan and BLP instruments and demand estimation literature using aspects of other firms to instrument for a given firm's decisions. These instruments require the Ally-Pecos style information and timing assumptions. You couldn't just do this without the timing assumptions. Generally speaking, Gunter's capital stock is going to be correlated with my omega, my productivity shock. It's determined in some dynamic decision problem. I've been saying that Gunter's fixed input and his productivity shock are potential instruments for my variable input. Uh, this is a little bit weird because it's not directly observed, but in these models, it is observed conditional on parameters, so it can be in the instrument set. And this I already sort of mentioned. Okay, so the last point of the paper, given this idea, this thought of using these competitive instruments, is to think about how best to use them. Right? Let's imagine we're in Cornell. Let's imagine we have markets with like 10 competitors. There's one fixed input. And following my discussion, we actually have 20 instruments for my variable input. The capital stocks for all the other 10 firms I'm facing, and the lag productivity shocks of all these firms. Of course, from an asymptotic perspective, you could just use all of them, plus maybe all functions of them. But from a small sample and numeric perspective, that's going to be problematic. You got weight matrix issues and small sample biases. Right? So what we're going to try to do is use some economic theory to reduce the dimension of instruments. Again, this has an analog and some recent stuff done in the demand estimation literature, and even going back to BLP, but recent papers trying to think about efficient instruments in demand. So I'm going to maybe talk about three ideas. The first is going to be the idea that if I just have a single competitor, there's two instruments, their fixed input and their productivity shock. But really, if they enter in the same way, I could sort of take those two instruments and combine them into one instrument. So I'm going to talk about that idea. Then I'm going to talk about combining Fs and Omegas across competitors, right? And try to compare it, reduce that to a single instrument. And then I'm going to ask a question which might be more relevant, which is what if we don't observe data on competitors? For 1 and 2, at least, we're going to make some additional assumptions on the model, like functional form assumptions on demand and the production function, but this is only an efficiency issue, right? If the assumptions are violated, these instruments are still fine. It's just whether they are the efficient instruments or not. So I'm going to make some somewhat heroic assumptions, but they're just for efficiency. Okay, so this is just saying that we're going to do this using Chamberlain's optimal instruments for results for conditional moments. Generally speaking, this is the formula for the optimal instrument, and this is sort of going to be very complicated, right? And so we're actually not going to get the entire optimal instrument. We're just going to get some restrictions on what the optimal instrument looks like. So this is the idea of combining for a single competitor. So here we're thinking about conditions where essentially the effect of my competitor's fixed input and productivity shock on my V depends only through some amalgam of those two things. And here it really sort of makes sense, right? If I think about my opponent's production function, if F and omega enter my opponent's production function just through this sum, then it should only be that sum that matters, right? And so there's this amalgam with one additional assumption that can be essentially, you don't need to have two instruments. You have one instrument, which is this, and you've now used theory because the production function looks like this. That is a reduction in the dimension of the instrument. But I'm not saying, and this relates to what I said before, I'm not saying this is the efficient instrument. I'm saying the efficient instrument is not a function of these two variables. It is just a function of this scalar here. Right? I still don't know what the exact form of the optimal instrument looks like. Depends on demand and conduct and things I don't know. Next thing is combining across competitors. So in a similar way, we're trying to think about conditions under which the efficient instrument depends on now a vector of stuff I've now added for each of my competitors. Only the sum of those things matter. But if I have 10 competitors, I now have this 10 vector of things. And is there some scalar summary statistic of those 10 things that the optimal instrument is a function of? Right? Sort of like, you could go there and just add up your competitors' things and use that as the instrument, but there's no grounding for that. Right? I'm trying to come up with a grounding for some functional form in which I can take those 10 instruments or 20 instruments and sort of combine them into a scalar. Which again, not the optimal instrument, but the optimal instrument is a function of just that scalar. So We did come up with a way of doing this. It's actually more complicated than one thing. You cannot get this with sort of standard Cournot equilibrium. So the conditions on the prior slide, Cobb-Douglas demand, Cobb-Douglas production, linear demand, although it doesn't matter what these things are. And the key thing is this sort of behavioral model of beliefs. Again, you don't need to believe this is only for efficiency. This thing is everybody thinks, everybody else is like them. So it's a model, remember, this is a model implicitly we're thinking about here where everybody has different marginal costs or marginal cost functions actually in the industry. And so it's like, I'm here and I know everybody has a different marginal cost function. I know all your marginal cost functions. I think each of you behave as if everybody else has the same marginal cost function as you. So I think I'm smarter than all you. Each of you think you're smarter than me and everybody else. And so it's a little bit like these level K rationality sort of things. Anyway, sort of interesting because it sort of turns actually a complicated game. I mean, Cournot with heterogeneous firms and non-constant marginal costs, they're generally not analytic solutions to this. This sort of turns it easy because everybody's sort of playing best response to people who are playing in imagined homogeneous games is sort of the intuition about why this works. Anyway, if all that stuff is true, then this S function is this thing. That is, we have this aggregator that only depends on the structural parameters of the production function. It doesn't depend on the demand parameters. It doesn't depend on on other potential conduct parameters. Right? It's just this, right? We need, as one of the restrictions here, we can't have it depend on any unidentified parameters. So that's, if you believe your model might be somewhat close to this, this is a reasonable way to aggregate stuff. There is a model that's consistent with this, unlike just maybe adding these things up over firms. A few more things. Suppose one doesn't have data on the entire set of firms in the same market. You don't have data on all firms. You have data on all firms, so you don't know who's in the same market. So you can't form these competitive instruments. An interesting point is that while GNR showed under perfect competition, lag variable input is a useful instrument. With imperfect competition, lag variable input actually can be useful. And the reason is because of sort of the same logic, so that my lag variable input depended on my competitor's lag stuff. My competitor's lag stuff is correlated with my competitor's current stuff, and that sort of channel means that lag V can be a valid instrument. Right? And of course, you might think this is just sort of an imperfect instrument, that directly observing my competitors should be better, but there's a little bit of a Monte Carlo surprise in a second, which I don't really have time to get to. I'll present it very quickly. One last thing, this approach for identification can be problematic with multiple V's. I just want to point out, and we have a result in the paper that actually this really only works for one variable input. It'd be a problem if firms all had two variable inputs, and the intuition there is that a firm's choice of how much of each of the two variable inputs to use is really only based on the firm's own sort of price, the costs of those inputs. It's not going to depend on the competitor at all. So you need to combine this with other sources of identification if you had multiple variable inputs. Monte Carlo, just really quick, I'll just do the first one. The first one is just comparing with some data generated to mimic sort of a real world data set, is comparing if you do observe the competitor versus if you don't observe the competitor and you have to use this lag V. And so we have a bunch of duopolies. Again, this is inspired from a real world data set. I just have this, again, simple setup where I just have to do two-stage least squares because I'm going to assume this thing is observed, but I don't think that's going to change that much. The key here is just to evaluate what happens when we instrument for this VJ1 with the various different competitive instruments. Either we actually use the F and the omega of the competitor or we use V0. And all the coefficient estimates are close to the truth. So this is only all in the table. It's just going to be standard errors. Note, by the way, that this Monte Carlo setup, if these were monopoly markets other than duopoly, it would follow the GNR critique and things wouldn't be identified. So only the competition here that is allowing this thing to be identified. Okay, so this is the last thing I'll do. These are the standard errors. There's two possible instruments that are used. First, the lagged V instrument. If you don't observe competitors, this is if you do observe competitors. The sort of Monte Carlo surprise that I sort of was like, what's going on when I first saw this? Just stick in that Z, and actually the standard error is lower using lagged V. And it took a little while to figure out why this is going on. And it is related to the fact that, again, these are not the optimal instruments. Just the optimal instruments are functions of these scalars. And so this is not the optimal instrument. So we decided, well, if you really want the optimal, you need to put in all functions of these scalars to get the real optimal instrument. So that's essentially what I'm doing here. And you can see by the end, this instrument is superior. To me, though, the interesting, I mean, that would be predicted because this is sort of more direct. But the interesting thing is why this is lower than this. And I think it's because lag V has this nice property, and it's in some sense it has the right form, right? Because the way that lagged V depends on the competitor's lag stuff is sort of, if everything is stable in the market, is going to be very similar to how current V depends on current competitor stuff. So it's in some sense, when you have no idea what the functional form is and you just stick into some scalar, this is actually getting the functional form in the optimal instrument a little bit better than just this, which is just, yeah. Anyway, it's interesting also, I think, in this that given real data that lag V only does about 10% worse in terms of precision. Okay, so I want to show you the other part of the Monte Carlo, and I'll just conclude. So what's the point here? Again, assessing the impact of imperfect competition on these common methods. For many situations, it provides exogenous variation that's helpful for this stuff. It can work with Ali-Pekka style inversions. It can work with these other methods. And theory can be useful at sort of thinking about how to optimally use it. Also brings up this point that lag variable inputs, which had sort of fallen a little bit out of favor, is instruments can be sort of a little bit more theoretically founded. So thank you very much.
Hey Dan, really, really interesting. One of the hard things about moving away from perfect competition is just prices, like just different prices, which I know is a big topic in this literature too. But like,
Which is not covered here, but
but so I'm just like, how do you like how to conceptualize that in relation to like we move away from perfect competition? Okay, we have like new identification problems and opportunities, but at the same time, we got to deal with these like pesky like measurement issues. So just do you have a stance or a take on that?
I do have a little bit of it. I mean, I think, this is sort of an issue. Do you observe physical quantities that firms are producing, or do you observe revenues? Because often you are observing revenues. Now, often you get like things like price deflators, and you can try to convert those into physical quantities. Uh, Now, people have there's some recent work saying, you need to be really careful when you're using revenue. And there's a fair point there. On the other hand, I worry sometimes that a takeaway from this literature is you definitely, if you have quantities, definitely use quantities. And I don't not think that that is a good idea because quantities are very often very hard to compare across firms, right? At least with revenues, you have something, a dollar, a euro that is comparable. In fact, I didn't go through this, but we do have a sort of a model in this paper where actually quantities, if you had quantity data is vacuous, because people are selling like paper towels or something, and some people are selling it in 3-packs and some people are selling it in 2-packs. You as the econometrician don't observe that, so the firms report quantities, but it's really vacuous because you don't know how many rolls or anything. And in that case, you know, you want to use revenue, you don't want to use quantities, and some of these things will work. Like if it's a Cournot model and you have a price index, if you get from the BLS how much is paper towels now relative to they were last year, you can deflate it and this stuff will work. And there you would absolutely want to use revenues.
One more if it's quick.
Yeah, it just doesn't coincide with a lot of the markup stuff because then you're not going to get any of the market stuff.
Okay, thanks very much, everyone.
Thank you.
Yeah.